Because our crust is solid, rigid rock, when it's under pressure, it's going to deform. It's going to change in its shape, and it's where it's located, and its orientation, which direction it's facing. So we can see that depending on the type of material, some materials are going to bend. They're going to fold, like we can see in this image, where the layers of this rock have now folded upwards towards the center. Or if it's a rock that's really kind of fragile, it can fault, it can break if there's too much pressure on that rock. So when we're looking at our geologic structures on the surface, we can use them to figure out what Earth's tectonic history was like. Seeing this folded rock here on the image, I know that something has happened in the history of this area to cause it to go from those nice horizontal patterns in our sedimentary rocks, since it's been deformed into this folded or curved rock. The reason why our surface deforms is all due to stress. And stress is just force over an area. It's pressure that's applied in some way. If we're applying pressure equally in all directions, this is called confining pressure. And with this, it doesn't cause deformation. Instead, it just causes it to shrink in size, but it remains its overall shape. However, when we're looking at deformation, when we're changing the size and the shape of a rock, it's caused by differential stress. This is where we're going to have pressure or force in one direction stronger than in another direction. So instead of having equal pressure in all directions, I could squeeze something in from two different sides, and that would be differential stress. And we're going to see that there are three types of differential stress that causes deformation or change. And these are compression, where we're squeezing in from two sides. It can be from tension, where we're pulling it away in two directions, or from shear, where we're trying to move it in two different directions horizontally. This diagram is showing us our different types of stress. It's showing us using a six-sided box. So with confining pressure, all six sides of this box have the same amount of pressure. It will not deform it, it's just going to cause it to get smaller in size. So confining pressure is not deformation. The following three are deformation. So here at B, we're looking at compression. Now we're only applying stress to two sides of this box, and we're going to compress it. We're going to push those sides together. And we typically see compressional stress in areas with our convergent plate boundaries, where we have two plates colliding or compressing together, and this creates our mountain ranges. Our second type of stress is called tensional stress, and this is where we're stretching an object out in two different directions. We typically see these around our divergent plate boundaries, around our mid-ocean ridges, and our rift zones on top of the continents. And then our final type of deformation comes from shear stress. And here we can see that the box isn't being squeezed or pulled apart. Instead, the top of the box is being pulled to the right and the bottom is pulled to the left. This is called shearing. This shear stress is associated with our transform boundaries that are sliding past each other, and the San Andreas Fault is a really good example of this. Rocks behave to stress in a very similar way to a hair tie or just a normal rubber band. If I have a rubber band and I apply a little bit of stress to it, I start stretching it out, I'm going to change the size and the shape of that rubber band. If I apply a little bit of stress, it's not a big issue. When I remove the stress, it'll go back to that original size and shape. But if I apply too much stress, if I start pulling this way too far, let's say I try to stretch it a foot, now it's going to be too much stress. The elastic limit in that rubber band is going to break, and it's going to cause deformation. Now, with too much stress, once I stop squeezing it, it will never go back to its original size and shape. Instead, I'm either going to have a stretched out hair tie, or it's going to be broken, so it's no longer a band at all. So we see that rocks do the same thing. Under a little bit of stress, the rocks are going to change their size and shape. If we remove that stress from like an earthquake, those rocks will be undeformed. But if we apply too much pressure, they can either break or bend over time. And we'll see that the strength of the rock is going to determine whether it breaks or bends. Warmer rocks are going to behave more like a ductile substance. They're going to bend, kind of like you can bend Play-Doh. But when we're looking at cooler rocks, these are going to end up with brittle deformation. This happens when something simply breaks, and I like to think about peanut brittle. If you've ever tried to break off a piece, you can't bend it. It's simply just going to break, just like a very cold rock would. But we also see that the type of rock and the time that stress was applied is also going to determine whether rocks bend or break. When we look at rocks that are under stress, they're either going to deform in a brittle or a ductile way. Remember, ductile means that it can bend, brittle means that it breaks. So starting off with our brittle deformation, once we have a rock where too much stress has been applied, it's going to result in fractures. That rock is simply going to break into multiple pieces, and this usually happens right along the surface of the earth where it's colder and there's less pressure involved. The rocks are simply going to break just like peanut brittle does. But if we start going deeper into the earth where there is higher pressure and higher temperatures, we're going to see a different type of deformation that's called ductile. Now, instead of those rocks simply breaking, they're going to change their size and shape by breaking the chemical bonds. This is going to allow the rocks to bend, very similar to like saltwater taffy or Play-Doh.